Hi there, in this video we're going to go over another derivation of the Laplace transform. This is one that I tend to prefer. Now I've put a link down below showing you exactly where I got this from. Okay, so when we looked at the original derivation of the Fourier transform, we thought about two vectors. So say we had vector A and vector B. Okay, and when we did the dot product in vector A, B, we had A1, B1 plus A2, B2 plus all the way along to AN, BN, and we could also write that as the size of A times the size of B times the cos of the angle in between them. Okay, so that there was the dot product for two vectors. I've got that derived in the snippet section, so if you get in the snippet section you'll see that full derivation. Now when we thought about the Fourier transform, we thought about functions as vectors, so we were able to create a generalized inner product, okay, so of two functions. So see, we'll call the function f and a function k. Then this inner product would be, well, the summation would be replaced by an integral. Okay, so we'll just go from, just say 2 points A to a point B of a function, and we'll make it a function of time, f of t times k of t by dt. Okay, so that there is our inner product. Now we could think about this here as a function here that we're trying to approximate, and we can think about this here, our k of t is forming an orthonormal basis. So what we're going to do here is the same as the dot product. A dot b, say, takes the projection of A in the direction of B. In this case here, we're taking the projection of a function f of t onto a set of orthonormal bases. Okay, so that k of t. Now you can go over that in previous videos if you go back to the first 2 or 3 videos, and you'll see all that explained. Now when we did the Fourier transform, we looked at the Fourier transform as the integral from minus infinity to infinity of a function f of t. Now this k of t that we used, the orthonormal basis, was e to the minus j omega t by dt. Okay, now if you like, we could think about this minus j omega, and if we replace this minus j omega with our value s, okay, now generally you won't see that written like this for the Fourier transform. I'm only writing it just so we can then derive just a generalized integral transform equation. Okay, so we could see that Fourier transform written as the integral from minus infinity to infinity of a function f of t times e to the minus st by dt. Now what we would then say is that we have a function k, okay, so I'll just put the brackets. The function is k equals e to the minus st. Now that's a function of the variable t, okay. Now this s here, which in effect is our j omega for the Fourier transform, this here is our parameter. Okay, so what we're really saying is that t is the variable, but s is a parameter, so you could pick a value for, say, omega, and then t ranges, okay, from minus infinity to infinity for that value of omega, okay, and that will give you some value for that integral, and then you could pick a different value for s, and you could keep picking different values for s, okay, and then let t, the variable, range. So in effect s is a parameter and your t is your variable, but don't go writing the Fourier transform like that, because that's not how they write it. They don't put in, they don't call it with minus s, okay, they only leave in the function e to the minus j omega. Okay, so that there is a kind of generalized way of writing that function. Now that little thing there is called, they call that a kernel. Okay. Right, so we can then say we can create a generalized integral transform if we write the integral from of our function, let's say f of t times k s of t by dt, and we go from some point A to some point B, okay, and that there is going to give us some function f of s, right? So that there, and that's the reason why I prefer this method for derivation, is as a generalized inner product, okay, and we can choose different functions k, s of t, which would give us different different attributes for this this integral, okay. So excuse me. Now what we want to do then is, first of all, we want to note that we want this integral to converge, okay. We don't want it to head off to infinity, so what we want is, as the limit as t tends to infinity of this function f of t times k of st, we want that to equal 0 as t tends to infinity. Otherwise it's meaningless because it doesn't give us any value whenever we do the integration. Okay, now here's a main point here, that what we want to be able to do is we want to choose a particular criteria for this integral, okay. So what we want, one of the things that would be useful to be able to do is instead of differentiating in one domain, in the time domain, if we can ensure that differentiation of time domain would be equivalent to just multiplication in the complex frequency domain. So by complex frequency we mean S, okay, in that S domain, then that would be a useful quality for this to have, because it would then allow us to say, with differential equations, we could write the differential equation in the S domain and just do general algebra in the S domain, and then once we get the answer from the simple algebra, we could transfer it back to the time domain. So we've decided that that's one of the things we want to happen. So then what we have to do is we have to try and find out what this k of st looks like in order to ensure that that actually happens. So what we could do is we could say, well, we want to find the transform, okay, so we'll just call it t for the transform of the differential of our function f, and we want to ensure that that equals the s times the original transform of original function, okay. So we want to try and we want to try and find a function ks of t that ensures that this occurs, okay. So it just ensures that when we differentiate a function in the time domain, it's equivalent to taking the transferred function and multiplying it by our value of s, okay. So one of the things that we want to do is we want to make sure that we're dealing with purely causal signals, okay. So what we'll do is we'll restrict our time domain to be values from 0 to infinity, okay. So it means that we can rewrite this equation here in terms of our transform, and our transform is just written in this format here, okay. So let's go ahead and do that now. So what we're going to have is an integral from t equals, and I'll put t so you remember it's t we're doing it by, t equals 0 to infinity of our, it's going to be k to the st times, and our function there is going to be d by dx of f, d by df of x, sorry, d by dx of our function f, okay, all by dt, and we want that, so that's the left hand side, we want that to equal the transform of the function times s, so we can, there's our s there. Now the transform of the function again is integral from 0 to infinity over k of st times our function f all by dt. Okay, so that's just a statement there of what we want to occur. Okay, so we know that s is independent of t. Okay, s is just a parameter, so we can then take the s inside that. So I won't write it all out again, I'll just rub that bit out, and we can say we can take the s inside this integral sign. Okay, so then what we're going to do is we're going to do integration by parts on this. Now I've got a video section in the snippet section on integration by parts. So what we're really just talking it way through is what we want to be able to do is, in the right hand side we've got a function f, but on the left hand side we've got, it's not a function of f, it's a function of the derivative of f. Now by using the integration by parts, what we can do is we can split this up so that we can take the f out, so we'll just get a function of f, and when we take the f out, this function here, k of st, it will then go inside and it will become the differential. Okay, so that's what we're doing, and the reason why we're doing this, once we've done that, we can bring the f out and this f can cancel with this f, and we can cancel out the integral signs as well, and we're left with a little differential equation which we can solve. Okay, so I would recommend you go and have a look at the integration by parts in the snippet section if you're unsure of this. So what we're going to really have is, if we say, well, integration by parts, it would be if you had u dv, the integral of u dv equals u times v minus the integral of v du. Okay, and so we've let our u would equal our k of st. Okay, and our dv would equal d by dt of our function f. Okay, so we work through this here for this. Now I'll rub that out again, okay, because again you can check it out in that video if you're unsure about it. Okay, so that's just the general way of writing the integration by parts. So we're going to end up with our a value of u, which is going to be k of st times v, which is going to be our f of t. Okay, because we were using dv, so in order to get the actual value of v, we've got to integrate it again. So we're integrating that back, so we actually end up with our f of t, and that's going to be from 0 to infinity, and we're going to take away, so it's minus the integral from 0 to infinity. Now it's going to be our d by partial t k of st times our function f of t all by dt. Now it's the partial by partial t because k has got two components, got an s and a t, so you could differentiate with respect to s or t. And in this instance we're differentiating with respect to t, so we have to put down and change the differential to the partial differential. Okay, so we can then, if we look at that again, we can then rewrite this. Okay, and we know that from what we did up here, that the limit as t tends to infinity of this product equals 0. Okay, so it means that the first part here, this part here is going to equal 0, and then what we're going to do is we're going to take away the rest. So we're going to end up with minus k of s of, and t is going to be 0, times f of 0, and we're going to equal, sorry, it's going to be, if we put in change that to a plus sign, okay, and we'll take the negative inside the integral, so it's minus partial by partial t of k of st, right, all times, I'll put a bracket around there, all times our function of t by dt. Okay, so what we can do then is we'll deal with this bit later. Okay, so we'll leave that there just for now, and what we'll do is we'll put this back in for the left hand side here, and we'll make it equal the right hand side, so we just end up with those left hand side equaling the right hand side. So we'll have the integral from 0 to infinity over s times ks of t times a function f of t by dt. So that's just the right hand side of our equation up here, and now the integration by parts here, that's the left hand side. Okay, so that's going to equal the integral from 0 to infinity over minus partial by partial t of k of s t times a function f of t by dt. Okay, now what we can do is now, and the reason for doing this whole integration by parts is we've now taken that f of t outside that differential. Okay, so it allows us to cancel this f of t with the f of t outside the differential. So you can see that there. We've now got the f of t outside the differential here, so we can cancel that and cancel that. Okay, now the limits of integration are the same in both ends, so all we're interested in is what's inside the integral sign. So inside the integral sign, what we're going to have is our s times some function k of the parameter s and the variable t, and we're saying that there is going to equal the partial by partial t of our function k of st. Now what we have there is a little differential equation. Okay, so what I can do is we'll maybe pop this round the other side and take the negative over, okay, so it becomes more apparent. So we can have partial by partial t of a function k of the parameter s and the variable t equals minus s times k of s t. Okay, so that's a little differential equation that we have. Now you can work out the answer to that quite quickly, because we're looking for a function that whenever you differentiate it, you end up with the same function but just times a constant value s. Now that there is k of st. The solution to that is e to the minus st. Okay, because if you put e to the minus st in here for this, if you differentiate e to the minus st with respect to t, you'll get minus s e to the minus st. So we know that the kernel that we must choose in order to ensure that the differentiation in the time domain is equivalent to a multiplication in the frequency domain, that kernel we must choose to ensure that is the function e to the minus st. Okay, so it means that then we can rewrite and we can say, well, we know that the generalized integral transform can now be changed, and it will now look like t equals 0 to infinity of our function f of t, and our kernel k to the st is now replaced by e to the minus st by dt, and that there is our Laplace transform. Okay, now I like that derivation. Once you get used to looking at once you get used to looking at the derivation here, you can run through it actually quite quickly. So once you get used to looking at integration by parts, sorry, I can actually get through most of that and miss out most of the actual calculation lines. I've just put them in just so you can physically see them. Okay. One other thing I meant to cover as well, this part here that we left out, the k of s at 0 for f of 0, well, that's just going to be our value f of 0. Okay, so it's going to be minus f of 0. So the final Laplace transform you're going to end up with, if I put in that for Laplace transform, the Laplace transform of d by dt over function f is going to equal, well, it's s times the Laplace transform of the original function f minus f at 0. Okay, so that there will be our final Laplace transform of the differential. Okay, so that's all it is for that now. The next videos I'll go on and we'll go through some examples in order to see where we use this and the value of it. Okay, so thank you for listening and goodbye.